In fact, it is recording. As we'll probably hear this. Any, are you going to record this morning? That's how we'll introduce this one. Okay. Thank you very much. I see we've got 17 guys who have joined us. In a moment, I'm going to introduce you to our speaker. Well, let me just give you a quick quick rundown of Evan. Can you guys see this? Have I started sharing the screen with you or not? Not really. Okay. Evan qualified with BSc Geology in Rhodes University. And from 1969 to 2005, with 36 years, he started as an assistant geologist with PPC, and then he ended up until 2005 being the manager of Group Mining Services. After which he became a consultant geologist with Sepako Cement, and he was with them for from 2013 until 2016. Then he became a he became a consultant geologist in that last period with Asia Cement with Pakistan. And in 2016, for the last 4 years now, he's been retired and I think living in Stanford. So without further ado, I'm going to hand you over now to our friend Evan, so that he can, let me just see if I can get this on the line here. And he's going to run us through this interesting story. Evan, can you hear me?
Yeah, I can hear you fine, Henny.
And okay, then off you go.
Okay, great. There. Okay, thank you, Henny. Good morning, guys. As Henny says, I've been in this industry for pretty much all my life, 45 years of working business. And something shows me that you just never too old to learn, because I found out the other day, and that was from Henny, that there are apparently 330 billion particles.
Steady, Evan, you're moving around a lot.
1 kilogram of cement. So I'm learning something new from Henny. Thank you, Henny, about that. What I thought I'd do today is just start with questions that I'm quite often asked. And let me just get myself off the screen. All right. We've still got one on the screen there, Henny. All right. The questions that we still got one person on the screen.
Have we?
All right, I'll carry on.
Yeah, carry on. I'll take them off.
Okay, right. So questions that I'm very often asked, and that first of all is, how much cement does South Africa produce? Secondly, how much does a cement factory cost? And then really why cement is so expensive. This question comes because a lot of people have this feeling that you simply dig up some limestone, you crush it, and you sell it as cement, and you make one hell of a lot of money. So we'll talk a bit about that today. And then what is the difference between concrete, mortar, and cement? And then finally, a lot of people ask me, why does a cement company, or why do cement companies employ geologists? What the heck has geology got to do with cement? So I'll try and answer those first before we run through the process. How much cement do we produce? Well, South Africa has a cement capacity. Now, I've underlined capacity because not all of this is utilized today. It is an existing capacity. The capacity that South Africa has, 21.7 million tons. Now, if we look at that in terms of world production, we're sitting fairly down the line. South Africa, 21.7. We're not too bad, because below us over there is United Kingdom, 9.4. But just look at this other guy up here. That's China. Produces huge amounts in comparison to anybody else. The second is India. It doesn't even come to a third of what China produces. What does a cement plant cost? Well, the latest figures are it costs 2 billion rand per million tons of capacity output. The last two factories that were built in South Africa, SULPHURIC, of which I was part, that was in 2014, and that plant sits near to Overberg area. It produces 2.5 million tons. That cost 5 billion rand. And then Mamba Cement up near Tabazimbi, that cost 2.5 billion rand. Now, just as a side issue here, the SULPHURIC cement is 64% owned by Dangote, who's a Nigerian gentleman. And just as a story, he, at the age of 21, started a business by borrowing $3,000 from his uncle. And he took 3 weeks to pay back that $3,000. He is today the wealthiest man in Africa with a fortune of 14.1 billion US dollars. Not too bad, eh? The other thing is that lead times in the industry are very long. It takes at least 6 to 9 years from conception of a plant to the completion of it. The differences between mortar, cement, etc. Bear one thing in mind. Cement is just a chemical binder. It's actually purely a glue. That's all it is. And all the building structures that you see are made of concrete. Cement is just the glue that sticks together the aggregate and the sand. Mortar is just some sand and cement. And again, here, the cement is purely and utterly the glue that holds them together. So this is the cement pocket, gray stuff, which has got all those billions of particles according to Henny and Mrs. Google. And this is concrete, which is the mixture of the glue plus the aggregate and the sand. And that's what we see today as concrete buildings. And this is mortar, just the sand, etc. Then, why does a cement company employ geologists? Well, bearing in mind that cement is not something you dig out the ground. And a lot of people seem to think that. They think cement's very expensive because you just dig it out. It's not. It's a manufactured product. It is manufactured from a whole variety of various raw materials. And these raw materials all need to be located. They all need to be mined, etc. In South Africa, about 45 million tons of material is mined every year for cement manufacture. The raw materials that we use in cement are limestone, as most people would guess. That's the high proportion, 70%. Clay, shale, that gives us the alumina component. Iron ore gives us some iron to add to it. Gypsum, and the gypsum is added after the process. I'll discuss that a bit later. Limestone, as you can see, there is the largest portion, about 70%. Now, limestone is made up of a whole variety of minerals, including calcium, magnesium, alumina, silica, iron, etc., 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 and other miners. So, as we said, cement manufacture is really a chemical process, and therefore limestone suitability is determined by various chemical ratios and maximums. Now, the interesting thing here was, at university, my very, very worst subject by far was chemistry. And yet I've spent the rest of my life in the chemical industry because everything about cement is chemistry. Geology, nobody cares what you call the thing as long as the chemistry is correct. So how do we know what is a good limestone? And very often people think that a high-grade limestone is a great limestone for cement. The answer is no, it is not very much the case. Here we've got the components we're looking at. In the cement industry, we call something LSF. It's called a lime saturation factor, silica ratio, NaK, sodium equivalent. I'll discuss these a bit further. SO3 total and in here. Those are the factors which determine whether the raw materials are suitable for cement. Lime saturation factor is calculated by 100 times your CaO over 2.8 your silica, 1.18 your alumina, and 0.65 your iron. And we have got to control that in the cement industry to between 0.66 and 1.02 in your raw materials. Silica ratio, it's another thing that needs to be controlled, and that's calculated by your silica over your iron and alumina. That has got to be controlled between 2 and 3. Sodium equivalent, this is in the chemical, in the industry is known as NaK. It's Na2O plus 0.658 times your KGO. Here, it's a very important thing. Your maximum cannot be higher than 6%. If the NAK is higher than 6%, then you start getting into an alkaline cement. And as soon as you get into an alkaline cement, there's a good possibility of something called ASR, alkali silica reaction. And this reaction occurs between alkaline cement and certain aggregates, not all of them, certain aggregates. And it can take sometimes 15 to 20 years to manifest. What happens is,
Evan, can I just ask on behalf of the people, on your slide it says 0.6%, are you saying 6%?
0.6%, my apologies, is red. It is 0.6%.
Okay, and while I've interrupted, guys, if you have something urgent to say, put your hand up, there's a little hand sign. And or when we allow you to speak, just hold down your space bar, then you can also speak. Thank you for complying. Carry on. Thanks, Evan.
Okay, thank you. Anyhow, that is indeed important. It's not 6%, it is 0.6%. Now, what happens there is you get a reaction, and it's something that wasn't known 20, 30 years ago. One of the interesting things, if you just have a look and Google the Kariba Dam, you will see that the Kariba Dam wall is one of the latest things that is showing serious signs of ASR. And it is really weakening the dam. So let's hope we don't have problems there. But it is a very important thing, and it is often called concrete cancer. And that is all due to having a sodium equivalent higher than 0.6 in the cement. SO3, we've got to keep that at less than 3.3%, right? Magnesium oxide has got to be kept below 5. So you see there's a heck of a lot of control in what we consider to be cement grade limestone. Just have a look now at the cement manufacturing process. Cement plants can be quite large. A lot of people see a little blending plant down the road from them, and they think that that is a cement plant. It's not the case. Cement plants are quite big and expensive. The cement process we can break up into 4 basic components. And the one is your raw material processing. That's the side in which I was involved. The raw meal processing, your clinker processing, and your cement milling. Starting off with the raw material. In order to meet the requirements which we've discussed, it's often necessary to mine quite a few different mining operations simultaneously. You need to mine limestone, you need to get some silica, you need to get alumina, and all this material is then crushed and it is blended to try and meet those requirements that we've discussed. The blending is done in what is known as blending beds, where the material is stacked in windrows, as you can, let me show you up here, up and down the whole time, and it is, and it is then reclaimed at right angles to that. All of this is trying to blend out the variations. And you'll see the whole process throughout the cement plant. Almost everything is designed to eliminate variability in quality. Raw meal processing, once the raw material is crushed, it is now milled into a fine face powder. And final fine-tuning is now done by adding corrective materials with iron and a bit of silica at this point in time. The milling of this stuff is done by either a ball mill, more in the older days, and today we see more and more of these other ones, which are called vertical roller mills. You can see the size of the thing if you look at the people down the bottom here. Clinker processing, now is when the cooking process starts. First of all, we have this preheating. Now, when I joined the industry, there was nothing like a preheater. Today, these preheaters are used to try and gather all what used to be waste heat and use this waste heat to heat up the fine powder to about 1,000 degrees, even before it enters into the oven, which is the kiln. The kiln, it's this part at the bottom over here, and there's the preheater. So the powder comes down here and it is heated up to about 1,000 degrees before it enters the pipe here or tube, which is the kiln. The kiln is lined with refractory bricks and it is inclined away from the feed. And a cement kiln typically is about 3 to 5 meters in diameter and some 30 to 60 meters in length. It rotates quite slowly at about 3 to 5 times a minute, and it is fueled at the bottom over here by either coal, oil, or gas. In South Africa, mainly pulverized coal. This is blown into the kiln and it creates a huge flame, as you can see in the bottom right-hand corner, into that kiln. The raw meal, which is fed in the other end, then flows slowly down this kiln and it gets heated up to 1,450 degrees centigrade. It's an idea of what a kiln looks like. You can get some idea of the size by the humans standing over here. What happens in that process of clinkering? Well, the first thing that happens is that between 1,000 and 1300, water evaporation and calcining occurs. And this is the loss of CO2, carbon dioxide. We'll talk a bit about that later. Between 1300 and 1450, you get the formation of very, very unstable compounds, which are called halides and B-lights. And they react differently in longer or short term in the cement. I don't want to go into that too much in detail. What comes out at the end of this long tube of a kiln is stuff that is called clinker. And it's little balls, black materials you can see at the bottom. And if you break them up, it very much looks like glass inside. And that's all these very unstable compounds. And as we mentioned, clinkering results in the loss of ignition of about 60%. We move now to the final process, which is the milling and the storage. Incidentally, between those two processes, you've now lost 60% by volume. So you do not want to put your clinkering process far away from your raw materials because it means you're going to lose 60% of the material by CO2. Once you have clinkered the material, you've lost that, you can now transport. So very often your clinkering process and your milling process are located in separate areas or miles apart. Okay, your clinker can be stored and transported, and now they add 4 to 5% gypsum to it when they mill it, and this retards the setting. Otherwise, you often get flash setting in cement, and you can't really mix it. We now have a variety of additives that can be added to this, such as fly ash, limestone, and they're all extenders. They extend the volume of the cement. The cement is now stored in silos, etc., bagged and transported. That's what a bulk transporter looks like on the left. Down the bottom, you have what is called mini silos. And then on the top right, you have the bagged and the other variety of cements. I want to just touch very briefly on some of the changes and the improvements that have happened over the last 45 years of my life. The first of all, we'll look at CO2 emissions. This is quite a scary thing because 900 kilograms of CO2 per ton of cement. I think the cement industry is one of the worst producers of CO2. So a lot of blending has happened. When I started in the industry, there was an OPC, a cement, that was it. Today, there are a whole variety of blended cements, which all go to trying reducing the amount of actual CO2 in the final product. And these are the list of about 14 different types of cement that are available today, all with admixtures in them. Fuel efficiency is the thing that's really taken off, and that is, when I started, there were what was called wet kilns. Now, wet kilns meant that the raw material was slurried into a slurry and pumped into the kiln. And of course, you had to then dry off the water, which made those kilns very, very inefficient. Then they switched to dry kilns, which were far more efficient. So the heat consumption and a lot of work has been done today on heat, on the waste heat, which used to go to waste. Now it's all being recovered. We'll touch that a little bit. And then a lot of work has also gone recently into burning of waste products. So if that is our kiln down the bottom here and our preheater on the left, most of the work in the last 40 years has gone into this side, the left-hand side, the preheating and the use of that to not lose that amount of energy. If you look at the energy consumption in gigajoules per ton of clinker over the past, initially when I said we had wet kilns on the left, you can see they were using a huge amount of energy. Then it went to semi-dry, the preheater started improving, and on the very right-hand side, we've now got a fairly modern kiln. So you can see there's a huge saving in energy that has gone into production of cement. The other thing that has gone in relatively recently is to be able to recover the heat and to put this through into boilers and then to generate electricity and feed the electricity back into the plant. All this is in terms of trying to recover as much energy as you can out of your coal. If you look at the since 1970, you can see the improvement in the fuel efficiency of the modern kiln. Waste burning, I just want to touch on very briefly, and that is the use in the industry of things like tires, refuse, anything that has a calorific value, paper, wood chips, and other. And one of the more interesting ones that I can maybe just mention to you is this one, which I came across. And this is in my last job in Pakistan. Now, in the center over here, I'll go into a bit of detail. You can see on the bottom right-hand side is a pile of material, which is all the waste that they recover, and they put this in the kiln. In the middle center is the brown stuff. Now, I don't know if any of you have been to Pakistan, but if you ever went to Pakistan, you will discover one thing. You eat chicken all day long. Chicken, everything goes into chicken. That brown stuff is chicken shit, which they put in the kiln and they burn it. So on that note, I think I'll come to an end.
Thank you very much, Evan. And now, guys, to keep it orderly, if you can use the little hand signal that says you've got a question, then you can try unmute yourself by pressing the space bar, and then speak. So we can. I see John has already unmuted himself. So John will give you a first question. Then put up your hand if you want to speak next, and we can bring you in.
Thanks, Evan. That was excellent. Good to see that geologists play a role in supporting all these buildings of ours. Just tell us a little bit about SULPHURIC, which is the newest cement factory on the block, and I believe much more efficient and much lower cost to run than the old PPC and other plants.
Yeah, well, that plant initially I got involved fairly late on when I left PPC, and it was quite interesting because the SULPHURIC had nothing to do with cement. They were really into other minerals. So they had inherited a whole lot of limestone from Anglo-American, which they didn't know what to do with. So that was my job, to get them going onto cement. So it was a new plant, so it was very nice, because if you look, and I have some slides further on showing you the rest of the South African plant. Most of this African plant, other plant, is 30 to 35 to 40 years old. So it is in that inefficient zone. SULPHURIC were very lucky in the fact that, let's say, Dan Goat invested in it. I mean, he owns 64%. So he put in 3.2 billion Rand into that project. And it did mean that we could go for modern equipment, even though it is Chinese plant, it was very much more modern than anything else. The result is that they are able, or were able, to produce at a much better rate, and unfortunately undercut the industry and resulted in a bit of a price war.
And interestingly, completely built by the Chinese, lock, stock, and barrel.
That plant, every laborer, physical laborer, came from China. They built a complete Chinatown there. They refused to give any warranties or guarantees if they had to rely on any South African labor. So that tells you something.
Thanks.
Can I speak?
Yeah.
You referred to some of those ratios, the NAK and the others. Can you explain what the other ratios, why they're so important in cement?
Okay, a lot of them, the NAK is the one. The other one is, as soon as you go, let's say, for example, above 5% in your MGO, they start having all sorts of setting time problems in the cement. So the difference really between the modern cements and the old cements is the tight control they have on setting, because you can buy various cements that give you all sorts of results. Now, those have got to be very closely controlled in what minerals are in them, because every mineral affects something slightly. It affects setting times. You know, as I said, your gypsum, for example, sets your setting time so you don't get flash setting. So each one of those has a role to play. The one I just mentioned was the NAK, because that's a serious one. And if you produce a high alkaline cement, which we did in the old days, you've got very big problems of what they call concrete cancer today.
Evan, is it true that cement never stops hydrating?
That's quite correct, yes.
Can you tell me a little bit more about high alumina cement? We used to use it in the mines, and the reason we used them is that it caused less cement burn.
Oh, sorry, Henny, you're going to have to ask an expert on that. You know, there are so many varieties. As I said, there are about 20 or 30 different ones. And, you know, when they start looking at oil well cements and all those, they've all got very specific properties. You must remember I'm a geologist. Eh?
Gert, was your question answered there for you?
Have you got Gordon up? Gordon's hand is up, isn't it?
Yep. Can I ask a question?
Off you go.
Cement was originally, I believe, discovered, if that's the correct word, by the Romans probably 2,000 years ago. And some of their cement structures are apparently still visible, viewable. Has anyone looked at the composition of that cement and what made it so durable that it lasted 2 millennia?
Yeah, okay. What they did in the olden days, they used a huge amount of volcanic ash and pozzolan. And the pozzolans have got wonderful properties. Even today, they do add certain pozzolans to some of the things. The big hassle with that is that there are not that amount of volcanic ash and pozzolans throughout the world. So, and it appears when I looked it up that somewhere down the line, the Romans built all this stuff, but, sorry, are you asking something, Henny?
Yes, I want you to put your video on to have something to look at.
Okay, start my video. Sorry, Gordon, I'll be with you. Is that okay?
Okay, carry on, yes.
So apparently a lot of this technology was somehow lost. The Romans did do this and their structures were fantastic, but a lot of the technology got lost. But it is a huge amount of pozzolanic material that they used to get hold of quite easily. And apparently that material is not really readily available anymore, hence the move away onto Portland cement.
Sorry, so am I understanding you correctly that that cement was then fundamentally different from the current Portland cement?
It is very different to, well, it is different to Portland cement in the fact that it was almost all pozzolanic. And so it was a very different cement, but it had very good properties. And it is a bit confusing to me reading up because they seem to have lost the technology somewhere down the line afterwards, but it is very pozzolanic. And it required a very volcanic ash material to produce.
Well, thank you very much. If there were any, like in the future, we will have a backup meeting scheduled after this. If question time runs into that, I want to thank all of you guys for coming in. We had 20 participants at one stage. Before we go, I'd like to find out who JA2706657 is. All other guys have put their names in there, but James Bond has come here under J. Could you tell us a bit about yourself?
Henny, it's John Ager. I don't know how you changed the name on this thing. It's just that I'm using a company computer. That's my staff number or something.
Something similar to what Mandela used to wear. If there are no more questions.
No, Henny, can I just say thanks to Evan and thanks to you again for arranging it. Can you hear me?
Yes, we can hear you.
Okay, so thanks for an excellent job, and thanks, as I say, for organising the setup, and thanks everyone for contributing.
I think
we still have Gordon and Gert to ask questions. Gordon, you first.
Okay.
Sort of a related question to the Roman cement is Portland cement. Then, what is the lifespan? And if you were to build a best structure now using Portland cement, how long would that cement last? Given the comment earlier about it absorbing water and reacting and continuing to react through its lifespan.
Maybe I can answer that. I see you scratching your head, or do you know the answer, Evan?
Yes, go ahead, Eddie.
I did a lot of research, as I said, because I patented a product that shows that the presence of cement in a hole. And from what I could read up and hear is that cement keeps increasing in strength, providing it's a good cement. Specifically, even the marine ones become stronger and stronger unless there's something that attacks it, like cement, like a certain chemical that comes in. So yeah, the bottom line is cement increases in strength over time. Did you guys hear me on that?
Yeah.
Yeah, but it still doesn't answer the question, and that was, if we were to build a building now, and let's say we used the best cement available, how long could that last? Could we mimic what the Romans were able to do with their cement? That's really, in essence, where I'm heading with this.
Yeah, okay, if I can take that. Yeah, I think it's very much equivalent. And in most cases, if you talk to Mrs. Google or look at Mrs. Google, they'll say that the modern Portland cements are better than the Romans. I think the structures that are being built at the moment are also different, because most of them today are reinforced structures, which wasn't the case in the Romans. They didn't use that amount of steel in theirs. But I think, I don't know, there was a program on TV years ago which looked at the possibility in the next couple of million years what would be left, and they were all saying there'll be no man-made structures left. So I don't see us lasting as long as the pyramids did. But yes, to compare the two, the Portland cements of today are as good, if not better, than the Roman. Just the structures are quite different to what the Romans built. I don't know what would have happened had the Romans tried to build the Empire State Building or something like that.
But if I can come in there too, sorry, Harry and Gordon, I mean, a lot of it goes back, as you said, to the structure. If you look at those old Roman buildings and old English churches, I mean, the actual way the structure was done and the blocks were laid, I think played a big role as well. And it begs the question about Twin Towers. When those aircraft flew into them, they fell down, almost instantaneously. Obviously, there were other factors like heat and fire as well. So I guess, as you say, Evan, the structure is critical as well.
Yeah, I think also, I'm not sure of the exact thing, but today's modern engineering guys are cut back the cement to an absolute minimum, and they can do that because they know, and this is the biggest thing about having control in the quality. You know that if you build a building today, or if you build part of it and you build some tomorrow, the quality is exactly the same. I'm not sure if that was the case with older cements in the Roman times. But I guess what they did was they made sure the buildings didn't fall down by doubling up the amount of cement used, etc. Whereas today they will cut it down to an absolute minimum to get the required strength that they want.
Gordon, Gert had his hand up before you. Gert, do you still want to ask a question?
The Americans built a big highway through to Alaska in the winter because they were afraid of a possible Japanese invasion in Alaska. They also have to build structures in Antarctica. Now, apart from heating it, do you use a special cement in these cold conditions?
Yeah, they do use special types of cement, and I think one of the biggest problems is in the setting times of the cement. So it will be quite technical, but they would be using different types of cement. They're able to change the setting times quite rapidly and easily on cement. I'm not sure of that particular case, but yes, they would most certainly be using something very special there.
If I can come in here more locally, in the Drakensberg, when we did in Lesotho the tunnels, we also had to put the concrete to sleep, as they say. You put in a retarder, and then when it gets to the face, eventually you put an accelerator. Those treatments, they say, is not very healthy for the cement, but you know, you've got to work with what you get. So you can, as he says, you can extend the lifetime of the wet cement, and by putting it to sleep, and then you accelerate it and you get to use it.
Yeah.
A parting comment from me relating to your comment about cement being the glue is it's vitally important for engineers to make sure that the other components that are being glued together are correct. In a past life, I had projects in China, and there was a massive earthquake not far from the capital city of Sichuan province called Chengdu. And I had 2 employees there at the time who were about to board a plane. So they were at the local airport, which is about twice the size of OR Tambo, and they saw the ground coming towards them as a wave, as the P wave approached. Anyway, buildings sat down, predominantly 30 to 35-year-old buildings sat down on their basement floors or the first floor of the structures. Typically, they were 5, 6, 7-story high buildings, and they all sat down. And we, as part of the relief efforts, we went out to go and see if we could assist and see what the cause was as to why so many buildings sat down. And if one puts one's knuckles together, we found that most of the buildings had been built with uncrushed, rounded river cobbles about the size of a clenched fist. And they all acted as ball bearings against each other with very little cement between them. And when we pointed that out to the Chinese, that this was a building inspector issue and that the building standards had not been adhered to, they very quickly shuffled us away from those areas, although we got plenty of photographs of the fact that there was no quality control on the structural material that goes into a concrete building. In other words, the steel and or pulverized rock, crushed rock, angular rock, which is what you need. You need angular fragments, thumbnail-sized angular fragments to make good cement. Good concrete, sorry, good concrete. Cement being...
Yeah, Gordon, I mean, Evan will add to this. I mean, it goes back to the whole science of aggregates. I mean, you know, an aggregate, as you say, is not just, you know, round particles. It's a mixture of particles, and having a variety of size in those particles, I believe, is also critical. Evan,
aggregates is another whole subject. You know, the aggregates for concrete. But you know, for example, you get, let's say, the roads, people build roads, and in Europe, a lot of them start using a limestone, which is the worst thing to do because you get a polish. And so those roads end up with this very, very slippery surface. So yeah, any aggregate in any cement thing is very, very important. As John said, angular, round particles are the worst thing to use in a nice river sand, let's say, in a concrete. So you need angular particles.
To emphasize that point, the N2 was a concrete road for many years, probably about 2 decades. And eventually it degraded very badly because they had not done an analysis of what the aggregate was going to be that they put in. And it turned out to be olivine-rich rock. And the olivine degraded over a period of time, which degraded the quality of the cement, and the concrete road, the N2, broke up very rapidly, long before its expected lifespan, and it was eventually replaced by tar.
Yeah, they were using your leftover VIC material, weren't they, Gordon? Bushveld
I'm not
stuff.
sure where. Yeah, I'm not sure where they got their product from, but Stephen Davey presented a paper at UCT about a year ago in which this particular aspect was brought up.
See, Adrian has got his hand up. Adrian, I think you're going to be the last speaker. We'll run out in time in a minute unless they give us more. So if you can quickly...
So they've given you more, Henny.
Okay, just a very quick comment. I have a memory that in Welkom in the early 1960s, when they were building the municipal buildings, that they built the foundation concrete with mine waste which contained a lot of pyrite in it. And eventually the pyrite oxidized and formed acid, and that sort of destroyed the foundations. So just another thing about careful what you build with.
Yeah.
Okay.
Okay, guys, I think that's about it. Yeah, just to come back into that story of aggregate in the construction industry, that's why it's so important we look at the grading envelope and the curve of the aggregate so that we fill all the voids. I suppose we always used to say it makes you use less cement, but I suppose it is more to give you more surface to glue together. That's why you've got different size particles filling in the gaps.
Yeah.
Well, thank you very much, guys. I think that was fairly successful. We're down to 13 participants, so we're losing our audience here. If there are no more questions, then we're going to have another talk for you in a week's time.
Yeah, we'll get the program out in the next 24 hours, Henny. Thanks very much.
Thanks, everyone.
Yeah.
Thanks a lot.
Thank you.
Thank you.